throughout this chapter, you're going to be given more specific instructions to where they're going to say, all right, create a parallel circuit where you have 2 light bulbs and a switch, but when the switch is open, it only turns off 1 light bulb. Okay, so that's going to be coming kind of after. Oh, you did?
I wanted to say parallel, but only bulb B is on.
Oh, so it wasn't parallel though? Okay. Well, actually, it was that one you asked me about, right? I think that one was actually parallel. Well, it was a test. It was a test, okay? Why they would put that question in there when we hadn't even talked about the other kind, I don't know. Sometimes they keep you on your toes here in a little bit. I always forget about that question whenever I assign that. So it's no biggie. It's no biggie. You know, we're gonna learn about it here over the next couple of days. I just wanted to, it's kind of a challenge question. Okay. Anyway, now we are going to be talking about series and parallel circuits throughout the next couple of days. We are splitting this into 2 days. So when we're starting off with series, it's the more basic of the 2 types. Obviously, when you start getting into parallel, that's kind of more of the setups that you're going to see in households, or even newer Christmas lights. Are you old enough to remember when Christmas lights with 1 bulb out, the others would go?
Yeah.
You are? Wow.
Well, probably because people still use it.
Yeah, that's true. That's because they used to last, as long as you could find that bulb. Which they still have yet to make lights that are really easy to remove and replace bulbs. So, as you grow older, be thinking about poor Mr. Dorfler and his hands after a while aching because the invention for new lights and the ease to remove those lights just has not been invented. What's that? Whoa. Yeah, Grinch. Actually, I barely put up any this year just because of our schedule that we had. So a little disappointed in myself because every year I look forward to getting on the roof. But do I decorate what?
The outside of your house.
I put a little bit out this year. Usually, like I said, I really look forward to getting up on my roof for like 2 hours every year and leaning over the edge, putting those up around 75% of my house. But
I watched the guy do that, and I really thought he was about to just eat it, dude.
There have been times it was a little sketchy.
He was like on the side, but he was like standing up. I was like,
Yeah, there's a few times in my career doing that is I had to take a seat back like, oh boy, it really is. It's not too bad except when you get to over the garage because that's like the highest point almost, and also it's over concrete. And I tell you, it looks about double the size or double the distance when you're up there than it was when you're on the ground. Anyway, old light bulbs or old Christmas lights, as we said, when 1 light bulb would go out, they would all go out. You did the searching and everything like that. That was because they were all on a single string of wire. Okay? That's because they were wired in series. Now you look at those new lights where 1 goes out, the rest stay on. But now you have this wire going here, this wire going. They're all connected by multiple wires. That's because parallel circuits provide alternate pathways for the electricity to flow. So that's why a lot of times in houses, right now, if I were to turn all my lights on in this room to 3, I've got essentially 3 light receptacles that are out, but the rest remain on. That's because of the multiple pathways. And sometimes there are devices that, if they are wired in series, they do have a built-in bypass that allows for the electricity to still go over or through the damaged receptacle. But, you don't always see those, but they do exist. Anyway, in this section, what we're going to do is we are going to calculate the equivalent resistance. There's a term we've seen before. For a circuit of resistors in series, and find the current in and potential difference across each resistor in the circuit. Okay, so right there are three things that we've seen thus far in the previous chapter. And also that idea of finding the current in and potential difference across. Now, yesterday, I'm going to go back a few slides. That's not it. That's not it. Where was it? That's not it. That's not it. Where was it? Maybe I passed it. Okay, I'm going to find it. Oh, yeah, we started talking about this slide. Terminal voltage, potential difference across the load equals terminal voltage. Okay. Those concepts are going to start coming through when we start talking about this, when we calculate current in and potential difference across these resistors in the circuit. So when we get into the last section or two, I think there's 4 sections in here. I can't remember. We're going to be taking those concepts in a complex circuit. We're going to be building off of those. We're going to be identifying if the resistors are in series or parallel, and then using some of the notions we're going to be covering today, as well as tomorrow and early in the next week, to help calculate each of those current in and resistance or potential difference across a particular load. We're then going to calculate equivalent resistance for a circuit of resistors in parallel. That's what we're doing tomorrow. And again, we're going to find the current in and potential difference across each resistor in those circuits. Okay? So, resistors in series. What a series circuit is, it describes 2 or more components of a circuit that provide a single path for current. This right here, resistors in series carry the same circuit. Again, it's one of those statements where I have an asterisk, in this case, double asterisk. Okay, that is the notion that we have to keep in mind, especially when we get into complex circuitry. The equivalent resistance can be used to find the current in a circuit. And the equivalent resistance in a series circuit is the sum of the circuit's resistances. So that last statement right there is a good chunk of what we're going to be doing today. Okay? A lot of times we got to figure out the equivalent resistance first before we can calculate the current. Okay? We do that by simply adding them up. Straight on through, add them up, easy peasy. Okay? It's different for parallel circuits. Okay, just to kind of give you an idea, when we get that tomorrow, in order to calculate the equivalent resistance, we have to convert whatever resistance value we're given, convert them into fractions, and then take the inverse of that sum of fractions. It's a couple more steps, trust me. So yeah, you convert it into fractions. So say you have a resistor of 4 ohms. Okay, you then essentially convert that into a fraction of 1/4. Decimal value is what of 1/4? 0.25. Okay, so you got that. You then take that value and take the inverse. You take 1 divided by 0.25. That will be your equivalent resistance in a parallel circuit for that particular resistor. Right? It's not too bad. It's honestly not too bad. What I highly encourage you to do, though, is when you do calculate equivalent resistance for parallel circuits, you write them down. Write it down so you can see, because there's going to be a lot. It may look basic and simple, but it can get complicated if you don't have a visual to look at. Okay, that's tomorrow. That's a good way to end the week. Okay, so again, just a quick little schematic diagram and a real version of the schematic diagram where we have. I'm pretty sure you can tell what that is. It's a battery, and those are your resistors. I mean,
Why don't they have
that's a good question. The symbol for resistors is fairly universal, so you could use those. But I encourage you that when you are doing your schematic diagrams and it does call for a light bulb, actually use the circle around it. Okay. So 2 or more resistors in the actual circuit have the same effect on the current as one equivalent resistor. You know, I kind of wish I would have put that in asterisk as well. Basically, what this statement is saying is the same as this. Any resistor in a series circuit, you just sum them up to equal. It's going to be equivalent to one resistor equaling the sum of those. Okay? Let's talk fancy a little bit in here. The total current in a series circuit equals the potential difference divided by the equivalent resistance. Now, we should already have that formula in your formula sheet. Now, I don't care if you put it in there again, but you also might want to put in there the little heading for your formula sheet that says equivalent resistance in series, and put the formula for that down here at the bottom. Req is equal to R plus 1, R plus 2, yada, 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 if you want to. Sometimes as a friendly reminder to yourself, when you get there, that's what you need to do. Okay, so make sure you got that. So let's look at a sample problem. Yes. What's that? What was that DJ does that sound? I don't know. I don't know, folks. I'm trying to recover from my broken glass yesterday. I can't do it now. It's not natural. Anyway, speaking of yesterday, got better. Okay. So in third hour, I was, demonstrating the spectroscope, those tubes you saw up here, and I've always said it's like one of my most dangerous pieces of equipment. I made that true yesterday. I didn't break anything, but we had the lights out, and I was talking to them about, what we were observing and everything like that. I didn't realize that my pinky was as close as it was. So it came in contact with that metal terminal on top. Not only is it a metal terminal with electricity flowing through it, but if you look really closely, each one of those little glass deals has a little piece of metal that allows for arcing of electricity. That got me. And they thought I was faking. Well, I don't know why anybody think I'd be joking around like that. But it's like for like 5 minutes, my pinky just felt like it was asleep. It was really weird. I felt it all the way up my arm. But it was only like a split second. But it's interesting. All right. We have a 9-volt battery connected to 4 light bulbs. We are to find the equivalent resistance for the circuit as well as the current in the circuit. So, what do we know? We know that we've got a 9-volt battery. We know that we have a resistor. We get the resistor values from the image right here. It doesn't matter which order you go. I always tend to go in a clockwise fashion. In this case, it doesn't really matter. Okay, so we have a 2 ohm resistor, 4 ohm resistor, 5 ohm resistor, and lastly, a 7 ohm resistor. So we need to figure out first the equivalent resistance, because we're going to use that to calculate our current in this scenario. Okay, so again, there's your schematic diagram of that image from the previous slide. So again, we're going to use our summing powers to calculate the equivalent resistance in a series, and then use that formula to solve for current. Blah, blah, blah. So there you go. See how this slide kind of is all jacked up? Yeah. Tomorrow, when we do the parallel, I'm going to have to rewrite it on my whiteboard here. So basically what this is showing here is we're just adding up the 2, the 4, the 5, and the 7. Okay? You add those up, you get your first answer for the equivalent resistance of 18 ohms. And I'm really sad that they also didn't include the unit. Again, I can't change this. Okay? So don't forget, go ahead and add ohm here. That's our unit for, or your omega sign. And by the way, I noticed that on the last test, a lot of you were able to put the omega sign on there. Well, looky there. Okay, that's easy then. That's easy.
It's on Wikipedia. Free is like Wikipedia.
What?
The omega sign. Copy this from Wikipedia.
Oh, so you're saying you're going outside of the test
I did it beforehand. I copied it, then went to the test.
Y'all did that?
You know what I say?
I just wrote all.
I copied
that-
pasted the problem into Google and came up with the home sign.
You both are sus. And yes, I have played that game. My wife made it awesome because for like a night, we all sat around our house and played Among Us. And but my wife said she was tired of playing it, but she would hear my daughters talking to their friends, and she would get the code, and she'd get on there, and her name was Yo Mama, and so anytime she got the imposter, she'd just go and attack our daughters on there, and it was awesome. It took him until the next day. My wife's cracking up, but that's about it. I watch a lot of videos on it. I just don't ever play it. Don't need that stress in my life. Anyway, we go and calculate the current for that particular diagram. And we have a 9-volt battery. We calculate 18 ohms of resistance. We get 0.5 amps for our current. So, blah, blah, blah. So go back to the statement here. For resistors connected in series, the equivalent resistance should be greater than the largest resistance in the circuit. Our largest resistance in the circuit in this case was 7 ohm. So that's just a nice little check, evaluation tool to help us make sure that we've at least calculated to the correct manner. Okay. Next thing I want to do is, again, you probably saw this coming. I want you to open up your books to page 650. $650. Oh, that's really dark. Oh, that's because I don't have a whiteboard on there. Ha! Makes sense. Okay. And I'll see that, right? 650. All right. Let's look at, let's look at number 4. We're only going to do a couple because I think it's all pretty similar, but I'm going to try to show you a variety of examples that you might encounter for your homework this evening. So let's look at number 4. Okay. Number 4 says a series combination of 2 resistors, 7.25 ohm and 4.03 ohm, is connected to a 9-volt battery. A says calculate the equivalent resistance for the circuit and the current. Okay, well, first thing is we know that we have a 9-volt battery. Our R1 is 7.25 ohm. Didn't have to use Wikipedia for that. And R2 was 4.03 ohm. Okay, so first off, it's just simply going to be calculating equivalent resistance. So we get 7.25 ohm plus 4.03 ohm. And so what's our equivalent resistance here? 11.28 ohm. Okay. All right, so that's really all we have to do for A, was find the current. Now I know it says calculate the equivalent resistance of the circuit and the current, but we're not gonna. Well, you know what? Let's do that. Let's calculate the current. So again, it's delta V is equal to REQ. So we get 9.0 volts over 11.28. And so what is our current in here? What was that? 0.8 amps. Okay. So now let's look at B. B says, what is the potential difference across each resistor? Okay. So I'm going to write down my current over here just so I can keep track of that. And I'm not going to lie. I'm going to put what I had, 7.7. Thank you. 0.798. Okay. If you wanted to round it to 8, that's okay. Going back to the old rounding days. All right, so for B, though, we need to look at each individual resistor. And so we're going to be using the formula of delta V equals I times R. And so for R1, delta V is equal to 0.798 amps. R1 was 7.25 ohm. So what is the potential difference across R1? 5.79 volts. Okay. And again, this is early practice for what we're going to be doing next section, or last section, one of the next sections. Now let's look at R2. Okay. So again, 0.798 times R2 of 4.03. What is the potential difference across that particular resistor? 3.22 volts. So far, so good. All right. Next thing I want to do is look at number 5. A 7.0 ohm resistor is connected in series with another resistor and a 4.5 volt battery. The current in the circuit is 0.60 amps. Calculate the value of the unknown resistance. Okay? So, first off, what do we know? We know that our R1 is 7.0 ohms. We know that our potential difference is 4.5 volts. And we know that our I is equal to 0.60 amps. Okay? So other things, so what we're trying to find is R2. One of the things that we can start connecting is the fact that REQ, which is equal to R1 plus R2, is also going to be equal to, if we take that formula that we're using for current that involves all three of these and rearrange it, we're going to get the equivalent resistance is going to equal to delta V over I. And so when we set it up like this and remove the REQ label, we actually get R1 plus R2 is equal to delta V over I. Does everyone know how I got to this point? Okay. We're just relating formulas, substituting, okay, where necessary. And so R2 is what we need to figure out. And so if we go ahead and rearrange this, again, I like to show baby steps until I put stuff in there. I think you all know me that by now. R2 is equal to delta V over I minus R1. So now that I've got that situated to where I can solve for R2, I go ahead and start plugging in my values to where I get 4.5 volts over the current of 0.60 amps minus 7.0 ohm. And so, excuse me, we get R2 is going to be equal to what? What was that? 0.5 ohm. Questions on that? Question?
Oh, divided by 6?
Yeah, 0.6 amps. Okay. If there are no questions, then it is homework time. Those of you at home, you should have it posted to Classroom, so you can go ahead and work on that. It is 1 through 10. 1 through 10. And for those of you in class, I will go ahead and hand out hard copies. You will submit it to Classroom, though, however, by tomorrow. And I'm going to go ahead and end this recording.